Okay, guys, hi again. I think we can start now. And then today's chemistry, or rather physics, lesson will be on energy and change, right? So, this is also one of those, let me do this, one of those chapters in chemistry, or those sections in chemistry that are quite doable. So by the end of this lesson, we want to make sure we have covered all these points that I have listed here. This will ensure that at least you are proficient in this particular aspect of chemistry. Right, so we want to be able to define the heat of a reaction, also known as the enthalpy change. We want to be able to tell the difference between exothermic and endothermic reactions and classify these with reasons, right? And then the rest also including drawing and interpreting sketches and graphs of potential energy versus the cause of a reaction, right? So let us start. Let me do this. Okay. Not sure what happened here. Fix it. All right. So now, just before I continue, I want to make sure, am I audible? Can you guys hear me? I think there's a thumbs up there that you can react to, just to say that you can hear what I'm saying. Okay, I see a thumb there. All right. So now let us start. So some key definitions in this chapter. We'll start with them, and then as we progress, I'll keep elaborating what each of these mean in the context of what we are covering today. Now, what we want to know is, let me say, some key definitions. So the first thing I'd like to know is the heat of a reaction, right? These definitions are usually asked in your exams as well. So they might ask you, what is enthalpy change, or what is heat of reaction? Remember, heat of reaction and enthalpy change, it's one and the same thing. Heat of reaction, delta H. So for now, I'm just laying out all the definitions. Then, as we continue with the lesson, I'll make sure to include examples, to include the graphs and so on. And you can see how, you'll be able to see how these actually integrate. All right, so heat of a reaction, or the enthalpy change of a reaction, is typically defined as the energy absorbed or released per mole in a chemical reaction. So you would have it being energy absorbed or released Let's do this. In a chemical reaction. Now, I want us to pay attention to these keywords: absorbed or released. Chemical reaction. Right. Start with absorbed. We have absorbed. Absorbed. Let's make it red. Or released. Let's make this one orange. Right, you have these two keywords, absorbed or released. So in the case, or in the definition, heat of reaction. When we say the energy is absorbed, typically we mean that our heat of reaction, remember, is defined by the formula delta H is equals to H product, state change in the energy of product, state change in the energy of the reaction when we subtract the energy of products and reactants. Right. So during this mathematical, when computing this mathematical definition of heat of reaction, what we will notice is that delta H will either be greater than 0, or rather will be delta H, another will be positive, a positive value, or delta H, which is the heat of this reaction or the change in enthalpy, will be less than 0, or rather delta H. Remember, if it's less than 0, it just means it's negative. If it's greater than 0, it means that value is positive. Right. So if energy in a chemical reaction is absorbed, you'll find that your delta H will be positive. Let me do this. Come on. Okay, if energy is absorbed, delta H will be positive. However, if energy is released, delta H will be negative. Remember, if you are absorbing something, you are in essence growing in mass, in whatever you're growing. Like take, for instance, a sponge. If a sponge absorbs something, its mass will increase because now it's the mass of the sponge plus the water it has absorbed. If the sponge loses something, the mass will reduce, which is negative. Right. So in essence, that's what this definition entails. Right. Let me just try this again. Right. Here we are absorbing. And if energy is released in that chemical reaction, then delta H will be negative because we are losing energy. So that is usually what happens. So for now, we're just still focusing on their definitions. And then as we proceed, I will show you what these mean physically and in other examples as well. Right. Let's continue. Another definition that we have is an endothermic reaction. Endothermic. So what usually happens is you get two types of reactions. You either get an endothermic reaction or an exothermic reaction. So for an endothermic reaction, that's where you have energy being absorbed during the course of the reaction. Right. A typical example of this is if you take water and then you try to boil it to get water vapor, right? So the heat energy will be absorbed and so that it can break down the water molecules, and then water vapor can be released, right? And then, however, if you were doing the opposite, you're condensing water vapor to form water, you would find that you are releasing the heat energy because it's cooling down, and then you are forming water instead of water vapor. So that will be an exothermic reaction. So let me quickly write those for you. So exothermic reaction, energy is absorbed during the reaction. So Remember what we said, if energy is absorbed, our delta H, or the heat of that reaction, will therefore be positive. So, endothermic reaction, energy is absorbed. Right, energy is absorbed. Therefore, our delta H for this guy, for an endothermic reaction, tends to be greater than 0, or rather, because sometimes they represent it this way, or they can just say the delta H and they give you a positive value. Could be any value, could be plus 200 joules or something like that. Could be anything. So a positive value. Sometimes they won't put the positive won't be in front of the sign, but you know that if I give you a value and there's no negative sign in front of it, it basically means, or it automatically means that value is positive in this context. Right. So this would be your endothermic reaction. So this is how it would look like, right? Endothermic reaction. Now, what about the exothermic reaction? So we're just quickly focusing on, want to make sure these definitions are out of the way before we start our example. Exothermic reaction. In this one, it's the opposite of the endothermic reaction. It's basically, excuse me, energy is released in this one. Energy is released during the course of the reaction. So while the reaction is taking place, energy is released. Reaction. So remember what we said here. We said a typical example, e.g., if you take, let's say maybe you take ice and you turn it into water vapor, water, or you take water and you boil it to steam or water vapor. Remember, steam and water vapor is the same thing. These would be examples of an endothermic reaction, because you are putting in energy, or the system is absorbing energy in order to create the product. In this case, from us to move from ice to water, we add heat so that the ice melts, obviously, and then it breaks down the molecules or the atomic particles, and then from there you move to water. And then the other way around as well, if you have water and you move into steam, you would have to add some heat energy, and that heat energy is what gets these molecules agitated, and then they therefore move to, therefore the phase changes from water to steam. Right, exothermic reaction, you would do typically the opposite of these examples I just made for endothermic reaction. So for this one, we said energy will be released, right, during this reaction. So this is what you would get for an endothermic reaction. These types of enthalpy changes. You'll get an enthalpy change that is negative, because why? We are releasing, or we are losing heat to the environment. Right. So let's continue. So another thing I'd like to define is what you call activation energy. So this is just basically the minimum amount of energy you would need for you to actually start a reaction. So what that means is for any reaction to start or to take place, you must make sure that, or it needs a certain amount of energy. So since we made an example with taking ice and melting it to water, if you were to take ice, for instance, and add a small amount of heat, right? That ice might not necessarily change to water, even maybe not immediately, but eventually. But if you add a considerable amount of heat, you take this ice and you put it in heat that is about 100 degrees Celsius, for instance. Therefore, the heat energy at that point will be high, and therefore the ice will start melting to water. So in these two examples I just made, in one example, you add the lowest heat possible. Actually, not even heat at this point, you just put it in the fridge. The ice won't melt, right? Because it hasn't reached that minimum activation energy or that minimum energy it requires for it to melt to water. So for this water, for this ice to water reaction, it hasn't found that energy. But if you take the same ice and you put it in a hot surface where there's now heat, and then if that heat is enough, the ice will start melting to water. So that's what activation energy basically is. It's just the amount or the minimum needed for a reaction to occur. Right. So that is what you would call activation energy. Another typical example, if you were to take a car, let's say you have a car in any car actually, and the car is stuck, right? And you want to push the car so you can kickstart it or something like that. If you take your a baby or a toddler, that's like a very young toddler, say maybe the toddler is a year old, and you ask the toddler to push the car, chances are the car won't move, right? It won't go anywhere because the toddler just doesn't have enough energy to get the car to move. But if you take an adult, actually, if you make it bigger, take an adult that's I don't know, a weightlifter or something, and you ask him to put energy into pushing the car to move, chances are the car will move, even if it moves slightly. So that's what activation energy means. Basically, that minimum energy that is required for the reaction to occur. The reaction in this example being the car to move, and the energy being put in by either the toddler or the wrestler or the adult who's a bodybuilder or any other adult actually who can just push a car. Right. Now, let's go to the last definition I'd like to show you, activated complex. So this is usually called an unstable transition state from reactants to products in a chemical reaction. So what does it mean? So usually, let's say, remember, the particles in a solid are usually like this, just to make an example. They're tightly packed. If you remember in your grade 10, they said a solid has tightly packed. Right. It means in this solid, the bonds, let me just do this, solid particles, they're tightly packed together, right? So what happens now, imagine I want to start melting this solid. Let's say this solid was ice, right? And I want to melt this ice too. We'll melt it to form water. What will happen? During the course of this ice or this solid particle melting, these molecules, they will start breaking up, right? They'll start breaking up. The bonds between them will start breaking. So these molecules, they get excited, or the particles, they get excited. So what happens now is they are not as please mute yourself there. I think it's okay. Right. These molecules will be during the melting process, they will start breaking up. The bonds between them will start breaking up. So what happens is, let me just mute this, right? This person. Great. Right. So what happens now is when the bonds are breaking up, that state, that they achieve during the breaking up is called the activated complex. It's that unstable point where these molecules or these particles actually are breaking up their bonds so that they can form new products. I see I have a hand. I don't know, someone. Sorry, would you like to ask a question? And they will raise the hand. I'm not sure if you have a question. Okay. I assume that was a mistake. So that point in time is called the activated complex, right? So the typical definition of this would be, let me just note this. So whenever a reaction occurs, right, bonds get broken and new bonds form. So during the breaking and formation of new bonds, that state of the reaction is unstable. What's happening? Okay. So that state is called the activated complex. So lucky for you, you have to sort of memorize these definitions because in an exam, you are typically asked on defining them. From reactants to products. But it's very, very advisable to understand what the definitions mean. Right, to product. So like I said, when we move from reactants and we are forming new products, typically what happens, or what usually happens, is bonds get broken so that new bonds can be created to form new products. So another example of this is if you have, let me see if I can picture it for you. Let's say you have C and say it's like this. Let's make an example of methane. Right, methane is something like this. So these are bonds, right? These are bonds. This is a bond. That's a bond. All these are bonds. Everything that joins the carbon to the hydrogen atom is a bond, right? So what I'm saying is, if, for instance, you are burning methane, because methane is a flammable gas, if you're burning methane, what will happen is before we form the other products, because usually what will form is carbon dioxide and H2O, right? These will be the products that will form. So during this burning, obviously you will add some oxygen. Oxygen is usually like this. That's your oxygen. Oxygen atoms there, they are bonded. Right, during this reaction, what will happen is for us to form these new products, or for these reactants to form these new products, bonds will have to be broken for the methane molecule so that the C can go to bond with the O, and the H's can bond with the other O's as well to form this water, right? But that's not the point of what I'm trying to make here. The point is At that point where we are breaking the bonds, where the reaction has reached that part where it's now breaking bonds to form new products, that part or that state, that period in time where that is happening, the reaction is currently unstable at that point. So that is what is called the activated complex. This, right? So that's basically what it means, because now the reactants are transitioning from being reactants to being products. So for them to transition from being reactants to being products, bonds must be broken. The old bonds must be broken, which are the old C to H bonds in this case for methane, and O to O bonds for oxygen. And the new bonds that must be formed are CO2 bonds between carbon and oxygen, which didn't exist before. If you check by our reactants here, they didn't exist before. And the new bonds of hydrogen to oxygen. So that's why these bonds, they get broken and then they get rearranged and so on. So during that state, that is an activated complex. Right. So that's the last of our definition I wanted you guys to show you. So now, let us come to, there's a famous graph that I would like to show you. So still on change, right? Del H. This is also known as the heat of a reaction. That's what enthalpy change is, right? Enthalpy change or heat of a reaction. Right. So we usually get a graph that looks like this to represent our reaction. Right. And then typically you'll find something like this, and then it goes all the way there, and then it goes all the way there, and then all the way there. Right? Something like this. So, and then what will happen is the axis will be labeled as always, potential energy, or something else. It can be potential energy per mole or something else. But these axes you will be given. You don't have to memorize them or anything. You just have to know what it means. And then you have your time, right? Usually time is in seconds. Now, in this graph, I want to illustrate all the definitions that we just covered. What usually happens is you'll find your reactants. Let me see. Your reactants will be here. Right? This first line represents your reactant. And these are your products, or the energy of your products. So the energy goes all the way there and there. Right, these would be labeled. Typically, you would find maybe they say here there's 100, and then here there's 300, right? Some numbers, and then let's say here the peak, they give you that it is, let's say it's 1,000, right? 1,000 joules, 1,000 joules per mole, whatever. It could be any of those energy values. Right, so this graph typically looks like this. So here, at this point, you have the energy of the reactants. And at this point, you have the energy of products, right? Here. Now, let me actually change this. right, so reactants and products, right? Okay, let's say you have something like that. So what usually happens is, remember, we said first things first, we have a delta H, which is our heat of reaction. So for this particular graph, delta H will be given by H product let's put it here, minus the reactants. The heat of the product minus the heat of the reactants. Remember, it's always like this. You don't change it and make it your own. Right, so this is what you would get. Now, in this particular example, if you take a look, you have that your energy of products is 100 and your energy of reactants is 300. This would give you, let's say, minus 200 joules, right? So based on our definition, we said if H is less than 0, that is our exothermic reaction. If H is greater than 0, that is our endothermic reaction. So delta H for this guy is definitely less than naught. Why? The energy of the product is lower than the energy of the reactants, as you can see in the graph. Another thing I'd like to show you again is what they would typically show you as well is you will get something like this being labeled. This arrow. This is what we want to know as well. So if you think about it, if you want to climb a hill, you would definitely need to pour on some energy for you to climb all over that hill, going all the way there, right? If you want to go climb Mount Everest like most people do, you would need a lot of energy for that. So that amount of energy that you need is what you would call your EA, your activation energy. So typically this arrow will either be put inside this curve or here. It's the same thing. Doesn't change a thing. It's the same thing. Let's make it that's your activation energy. Right. It's basically the same thing. You are measuring the energy it takes or the minimum amount of energy needed for the reaction to start. The minimum amount of energy you need to climb over that hill. Right. So that's your activation energy going forward. Right. So what do I mean by going forward? I just mean that from reactants to products. That's a forward reaction. Now, what if we want to know the energy, in this case, the activation energy? So EA would be, you take the difference between the energy of the reactants in this case to the maximum energy, because it's just a distance. So it's definitely be 1,000 minus 300. And this would be 700 in this case. So in this example, this reaction needs about 700 joules of energy for it to start. Right? If you don't have that amount of energy, this reaction won't go anywhere. Right. Then we have this other point here, the peak. Now this peak energy here is what you would call the activated complex. Right. That's what you would call the activated complex. Let's do this. No. Exothermic, meaning sorry. Released. Just to make sure, are you guys able to see the yellow? Because I know yellow can be a tricky color to see, especially for people who are colorblind and so on. Please just put a thumbs up there if you're able to see the yellow. Okay, thank you very much. I see thumbs. Right, so this is a typical situation of what an exothermic reaction would look like in these energy graphs. Right, so at this point, we have defined what an activated complex is. We know what an activation energy is. We know what the enthalpy change is, right? So the way I like to think about it in this curve, I just tell a story, right? So I said we need energy to climb this hill, which is our activation energy. We need a certain amount of energy. Otherwise, we won't be able to climb the hill, which in this case, our hill is the reaction. We won't be able to start the reaction. As soon as we gather up enough energy to climb this hill, we go up to the top there. Now, at the top, that's where now we have reached our destination, and we are now starting to either witness the beauty of the hill or whatever, the view and so on. So that point is your activated complex. That's where now the bonds are breaking up to form new products. Right, so new product in this case would be, you have a new view up there. Now you can see better than you were at the bottom of your hill. Right, that's how I usually think about it. And then obviously for for an endothermic reaction, the opposite will be true. Let's just do it fast. Right. Now we want to do an endothermic reaction. Paste. Actually, it's fine. Let's draw a new one. So you'd have a graph like this. You said this is time. Time can be in seconds, hours, minutes, whatever. But as soon as you see a unit of time, you know that we are talking about time. This is your potential energy. Right, and obviously it's also going up there. Now, so I hope you can see the difference here, right? These are still our reactants. right? These are our products, or the energy of our product. But now, compared to the other one we just did before, if you can check here, the energy of the product is greater than that of the reactants. So let's use the other. Say here you have about 200. Say here you have about 600. And let's say here you have about 1,100. Whatever, really, they can give you any, you can be given any energy. You just need to know the fundamental difference or the meaning of how to interpret, in terms of how to interpret this graph, right? So in this case, what would be the activation energy? Remember, the activation energy is the energy needed to climb this hill. We are climbing this hill, right? So we have to measure from where we are to the top, the peak of that hill. How much energy do we need to get there? Right? That's your EA, activation energy. And remember what I said, the arrow or this thing here, it can either be inside or they can put it, or it can be put here. Still the same thing, right? Nothing changes. So let me leave it there. All right, so this is your activation energy. So we'll calculate what they mean in this case, in our example. And then you also have your heat of reaction, also called the enthalpy. Enthalpy is, we said enthalpy is the H, the heat of the product, minus the heat of the reactants. In our case, in this example, it would be products are 200. Oh, sorry, not 200. Products are 600. We are reading from here, remember? From here, we just do that. Products are at 600. Minus reactants are at 200. And this would be 400 joules. Now, this is a positive value. Positive value. Unlike this one was a negative value. Right. So if it's a positive value, remember what we said. If H is positive, H is greater than 0, or delta H, sorry, is a positive value, this means we are dealing with an endothermic reaction. Also, it means energy is absorbed. Remember my example of the sponge? If you absorb energy, if the sponge absorbs water, it'll have more mass. So if you absorb energy, in this case, you will have more energy. So the product will have more energy than the reactants, because to form the product, energy was absorbed. Therefore, the final product will have more energy than when we started at the reactants. The opposite is true for exothermic. To form the product, we had to release energy. So therefore, the final product will have a lower energy than the reactants. Right. So let me color code it for you. I like color coding so that when you read at your own time these notes, you will be able to see what we were talking about, right? So this was, no? Right. So those are your products. And we said del H is greater than 0. Right? And we said if del H is greater than 0, this becomes our endothermic reaction. Energy is absorbed. So therefore, it's an endothermic reaction. So remember the example I made? I said a typical example, if you take water and you add heat to that water, heat energy. If you add enough heat energy, you will break those water particles. The water molecules, or they'll get agitated, right? So what happens now is it'll then transition into water vapor or gas. In a gas state, the particles are excited. They're everywhere, right? Because the bonds are not as they're not as tightly packed anymore. Those particles, due to the bonds being broken, right? So because you added energy to the water, the system absorbed that energy to create the new product, which is water vapor. So that's an example of a typical endothermic reaction. Now, I think activation energy was made it yellow or orange. I don't know what that color is. Right, and then same as this guy. Said this guy is our activation energy. Now let me see. What else did we want to share? Oh yes, this right here. Remember our delta H we're taking there. Let me use blue. This is our delta H. When we say delta H, this is what it means on the graph, because we take the difference between the energy of the product and that of the reactants. Same thing as here. This will be our delta H. Right. So that is typically, or that is everything you need to know about this graph. And remember, at this peak right here, you get your activated complex. You have reached your hill, and now you are seeing a new view compared to what you had when you started at the bottom of the hill. So you have reached that part of the reaction where bonds are being broken, things are a bit unstable. What if you trip over and fall in your hill? So activated complex. Aha. So that is everything you need to know about this graph. So what other people or other reactions typically do is you can reverse a reaction, remember. Some reactions are reversible. So usually you'll find that moving from, okay, let's say moving from reactants to products. If you move from reactants to products, we call this a forward reaction. That's a typical reaction. You're taking you're taking water, and then you're boiling it to form water vapor. You're moving from reactants to products. Now, what if you want to move backwards? You take the same water vapor, and now you want to move from products, which is the water vapor, for instance, it can be anything really, to the reactants. This is what you would call a reverse reaction. Right. What it means as well is if, let me see if I can draw it for you. Let me put it here. Right, let me take this curve right here. Hopefully it'll fit. Copy. Let's see. I hope it fits. Okay, you guys should be able to see it though. Let me see. Are you guys able to see this? It looks a bit small on my side, the curve. Looks a bit small. Okay, I'm assuming you also can't see it because no one is giving me a thumbs up there. So I'll just try and increase it. Let's do this. Aha. You should be able to see it now. Are you able to see it now? I think so. Okay. I'll assume you're able to see it. I don't know. So a forward reaction is like this one. If we take, let me remove all of this. We don't care about them anymore for now, for this example. So a forward reaction, you're basically moving that way. That way. Right? That's your forward reaction. You're moving that way from reactants to products. A reverse reaction, you take this diagram right here, and you move backwards. So your products become your reactants, and your reactants become your products. So what do I mean by this? Let me do this. This is one of the concepts in this particular section of the chapter. I think that's fine like this. Okay. And then that guy, forward reaction, reverse reaction. So what you would have is, let me take the same graph, right? You'd have this right here, right? So in this case, now what was your reactant becomes your product, and what was your product becomes your reactant. Now you are moving that way. You are reversing the direction. So what does it mean? It means for me to move from water, let's say you move from water to water vapor, right? If I was moving from water to water vapor, that would be my forward reaction. However, if I now move from water vapor and I'm going back, remember you can take water vapor and turn it into water, right? What do you do to do that? You just simply use the process of condensation, and then you would be able to form water from water vapor or from steam. Now you're moving from water vapor to water. That would be a reverse reaction. What does it mean as well? It means if we're going forward, our reaction is endothermic. We're absorbing energy to create the water vapor, at least in this example. And then if we go back and reverse the reaction, we are losing energy because we have to cool the water vapor because it's hot now. It has a lot of heat energy. And we form water. Water condenses and there's a condensation temperature. And then the heat is lost to form the new product, which is water. So we're just reversing the reaction. It's one of those concepts that you need to know for this particular chapter. or section of of energy and change. Right, so that's the part I wanted to illustrate as well. And then now we have explained what exothermic reactions are. We have explained what endothermic reactions are. We have explained the different type of either you're moving forward or to the reverse direction and what it means for your reaction. Right. Now let's say I want to show you just how much you have come for this lesson. We've done that. We've defined the heat of a reaction. I hope by now you understand what it means even practically. We've defined exothermic and endothermic reaction, and we've explained the difference. We've classified what this means as well. And also the signs. We've defined activation energy and activated complex. We've drawn and labeled these energy diagrams or graphs. So now let's see if we can get an example up here. A typical example. But before we move there, I'd like to define one last thing. In any reaction, or in some reaction, actually, some reactions have what we call catalyst. A catalyst. This thing right here. So what is a catalyst? Basically, it is just there to speed up the reaction. It does not necessarily react with any of your reactants. It is just there to speed up the reaction. What it does, speeds up the reaction. A typical example they it softens up quickly. So essentially what you're doing there, you are making sure that if it was going to take you 3 hours for the meat to be ready, you are speeding up the reaction so that now it takes maybe half the time or at least 80% of what it was going to take you. Right. So that's what a catalyst does. It speeds up the reaction. It does not necessarily react, participate, or react. Let me say participate in the reaction. I.e., it does not react together with the reactants to form new products. Right. So when do we use it? We use it if the activation energy is a bit too high for us to achieve. Right. Remember what we said, the activation energy is the amount of energy we need to start the reaction. So when the activation energy is a bit too high, the self connection is when the activation energy is a bit too high, that's when now we include a catalyst. So the catalyst will make sure that the reaction starts early and therefore will finish fast, will occur faster, right? Will be sped up. So how do you show this in the graphs we were drawing? Let's see. First of all, let's define it in official terms so that you can even use it in your exam or so on. A catalyst is basically a substance. Let's see, substance that increases the rate. Okay. The rate of a chemical reaction. Right. But remember, we said itself, it does not necessarily participate in the reaction. What that means is it doesn't undergo any permanent change. So without itself undergoing a permanent change, right? Unlike the reactants that are involved. It may look like it's a long definition, but trust me, it's not that long. In the exam, if they ask you what a catalyst is, this is a free 2 marks, right? So how it would look like in our graph, if the activation energy okay, this is too long. Let me see if I can activation energy too high, right? Means reaction right. Solves this. Which means that the reaction will now occur faster because the activation energy is reduced. Let me show you what it means in the diagrams we were drawing. All right, let's say you have, I won't label it, it won't be as detailed as the one we had before, but it will have enough detail to illustrate this point. Just wanted to do this. Right. So if we have a reaction like this, and now we have our activation energy going all the way up there and there, right? These are reactants, these are products. So what the catalyst does, it basically comes, let me draw a new one. And reduces, no, this peak. Let me make it exaggerated so you can never forget this. What is this thing doing? Okay. Right, good. So it does this. Notice one thing though. This point, the point where the reactions and the product starts and end for both graphs is the same. I'll explain why that is. So without catalyst, high EA. And then with catalyst, lower. Remember what we said? We said EA means activation energy. I'll write it here so that you don't forget. That's basically what it means. Right. So that you will see this. Now, this is what a catalyst does. So you want to climb this mountain, but you realize it'll take you forever to reach the peak. So what do? You use space boots. I don't know if there's such a thing. So you use space boots, or you take springs and attach them to your shoes so that when you walk, you climb at least twice the distance, right? So that lowers your activation energy. So the energy that you would need to climb all this hill, right? So therefore, you reach the top faster. So that's what a catalyst does. You see that the reaction requires a lot of energy for it to start. You add a catalyst so that the activation energy required to start the reaction is lowered, and therefore the reaction can occur faster. Right? Faster reaction. No, can't be black. It will confuse you. Good. Now, however, the EA, or the catalyst, actually does not change the heat that the system absorbs or releases to the environment. What do I mean by that? It will not affect I mean, the heat of energy or the enthalpy change will not be affected by the addition of a catalyst. That's why if you check, even though these two graphs, the one without a catalyst and the one with the catalyst, even though they have different activation energies, but they have the same start and end points, right? Because delta H will not be affected by the catalyst. So that's what it means. So let's see if we can do a quick example. Right. Let's come here and say a quick example. So now imagine if you had a reaction where you're burning something. Let me see. Let's do this. So a typical exam situation, you'd be given a chemical equation. Well, let's say they're burning methane. Now, this is not methane. Methane is CH4. That's methane, right? This is likely butane. This one. Yeah, this should be butane. Let's say you're burning butane. Remember, every combustion reaction, there's just oxygen there, and then you have carbon dioxide and water always being the products. Always, for any combustion reaction, combustion means you are burning something. You will get the reactant and oxygen, and there will always be water and carbon dioxide being released. That's just a side note, but that's not our point for now. So obviously this reaction would have to be balanced. If you put it, you would have, you can put a 2 here. So you'll probably need the CHO, CC, let's say an 8 here. By now you should know how to balance equations. So for this lesson, I won't really teach you that. It's not our main focus. And then I think this should be, okay. 8, okay, let's see. This should be 13. Right, so if you practice enough, you can balance equations quite easily. Right, but for today, we're not focusing on that. This is our reaction, right? In an exam, you would be given something like this, or a test. Obviously, there'd be follow-up questions after. And then, so to show you that we are talking about this chapter of this part of our, this section of physics, they would write something like this. Del H is, for this one, it will probably be less than 0 because it's a combustion. We're adding heat to get the product. So the system must absorb heat. All right, is it? And then what would happen is you would be asked, and I'm asking you this now, based on what we just did, is this reaction endothermic or exothermic? Right, if you think about it, your biggest clue here is this one. And the fact that this is a combustion reaction. So those are the two biggest clues. But your biggest visual clue that you can never go wrong with is this one. You are told that delta H is negative. So what does that mean? It means the reactants have a higher energy than the product. So what does that mean? it means energy is being released, right? Or I said absorbed earlier, my apologies. Energy is being released. Remember what we said here in our notes, where is it? Released. So delta H is negative. So therefore, your answer would simply be, since del H is not, energy is being released. You can even draw that curve I showed you, right? Therefore, reaction is exothermic. A typical example that you'd find as well is exothermic reactions. If you think about it, if you were to touch a release to the environment, right? If you were to touch a fire, for instance, if you touch fire, you would burn, right? There's too much heat energy there. That's because that reaction, that combustion reaction of fire, where fire is the product, right? That combustion reaction, it's releasing energy to the environment. So it's an exothermic reaction. Yes. Right. So let me say this is our example one. Example two, you might be told, it can come in many different forms actually. You might be told you have an experiment and reactants are mixed in a beaker, right? Let's say in an experiment, just a simple one, experiment, reactants and then for the last one, I think we should do an example from a past paper. In an experiment, reactants are mixed in a beaker, right? And they say the initial temperature is measured to be I'm just shortening it, means temperature, don't be confused, as 25 degrees, right? And the final temp after reaction is measured to be as, let's say as 21 degrees Celsius, right? What type of reaction is this? Is it exothermic or is it endothermic? Right. Initial temperature, 25 degrees. Final temperature, 21 degrees. So this tells us that there was a loss in the heat in this system to the surroundings. So if there's a loss in the heat in the surroundings, the temperature of the surroundings decreased. Therefore, this right here will be an endothermic reaction. Right. So what do I mean by that? Because this might be a bit confusing. When we started, the reactants were at 25 degrees Celsius. That's when we started, the initial temperature. The reactants are at 25 degrees Celsius. They have a high heat energy. And then the products have a lower heat energy. Okay, let me see. After the reaction, I keep making spelling mistakes. I'm sorry about that. This is reaction. Right. So again, in this experiment, you have reactants that are mixed in a beaker. So the initial temperature is measured as 25 degrees Celsius. Remember, when you measure this temperature, you are measuring from the environment. You are not in the reaction. And then now the final temperature is measured as 21 degrees Celsius. Now, the question is this an exo or an endothermic reaction? So if you are standing here and you realize a drop in temperature instead of an increase in temperature, unlike when you are with fire, remember, with fire you will witness an increase in temperature, you will automatically know that that is an endothermic reaction. However, if we were told that the temperature of the reactants was 25 degrees, and then, let me show you, the heat of the reactants, where's that graph that we had? Yes, here. If the heat of the reactants is higher than that of the product, you get a negative delta H. Right, that would be an exothermic, but that's because the heat of the reactants and the product is like that. But in this case, we're dealing with temperature. Temperature, we can only measure it in our surrounding. So that's why we can't necessarily say this is an exothermic reaction, because you would be tricked, or you'd be, not necessarily tricked, you'd be quick to think this was an exothermic reaction, but it's actually an endothermic reaction, because from the surrounding, which is where we are as the people measuring the temperature, the surrounding suddenly dropped in temperature, meaning energy was absorbed, or heat was absorbed from the surroundings. Why? Let me write it for you. Because this one can be a bit tricky for some people. But remember, the rule of thumb is if I'm in a surrounding and I witness that my temperature is rising, it means whatever reaction is occurring is exothermic, because it's releasing its heat to me and I can measure it rising. And if the other or the opposite happens, where I'm in a surrounding or I'm in an environment and I realize that it's suddenly getting colder and I feel that the temperature is dropping, it means whatever reaction I'm observing there is endothermic, because it's absorbing heat from the surroundings. Right. So I'm just writing exactly what I was saying. Right, good. So now, um, that is it for these examples. Now, let's see if we can use an example from a past paper. Right. Let's see if I still have that picture. Mm. So now, something. and so on. All right, so let me find an example first. I think I had one here from my past paper. The Yes, I think I found one. Just need to bring it aside. Just give me a second. Mhm. Okay. So let's add the image. All right, let's say you have this example right here. Okay, I hope you can see. So in this typical example, you are given methane, and it's combusting with to release carbon dioxide and water. So they give you the balanced equation as well, right? And then, okay, let's give it there. So they also give you the activation energy. As you have the activation energy, right? And you also have your okay, okay, good. So now remember what I said in a combustion, right? Think of it like fire. Combustion always means there will be heat that will be released to the surroundings, right? And then now, in this case, you are given methane, and methane obviously is combusting in the presence of oxygen to release carbon dioxide and water. And then you are being asked, is this reaction endothermic or is it exothermic? Right. One thing you will note is there's a plus 891 kilograms per mole that is added on the product side. Right. So just quickly give me do this. Yes, good. So is this reaction exothermic or endothermic? Number one, our reaction here is exothermic. Why? First of all, it's a combustion reaction. Two, combustion releases heat to the environment. Now, don't be confused. If this right here was given as del H, right, is plus, and that's right. If it was given like that, then we would use it to mean, well, this is probably an endothermic reaction. But that's not the case. This right here and that are not the same. Right. So what it means is in the product side, about this much of heat energy is released to the environment. So therefore, this is an endothermic reaction. So this plus right here is one of the products of this reaction. This. If you check all the products, right, all these products, all of them, you have carbon dioxide, you have water, and you have these heat energy that is being released to the environment. So this plus right here just means one of the products of this reaction is heat energy being released to the environment. If, however, it was given like this, I want you to be very careful here. Very careful. If it was given like this, okay, let me write it there actually. Note, be careful. Want to write it, okay. Please remember this, guys. It's very important. The heat that is released and the enthalpy change are not the same. Be careful. Is not right. It just means heat is being released. Or heat is a product. That's what it means. If, however, they had said delta H is equal to positive and then this number, then we would say, okay, this is an endothermic reaction, right? But this one, specifically, it's an exothermic reaction. So you had two clues here. The first clue is that this is a combustion. Combustion reactions are always exothermic, right? Combustion reactions are always exothermic. As soon as you see the word combustion, just know always exothermic. Let me write it for you. Yeah, that's fine. I don't like poor spelling. Good. So now, I hope this point is clear. It's very, very important. Be careful here. Now, 7.2. Explain why all chemical reactions need activation energy. So basically here, it's a fancy way of them asking you, what is activation energy? So activation energy is the minimum requirement. The minimum energy needed to start a reaction. So explain why all of them need this, because a reaction cannot start unless it receives its minimum required energy. A reaction cannot start is met. Right. There's no reaction that will begin if the activation energy is not reached. That's why all chemical reactions need that much, need activation energy. It's not possible for you to start a reaction without it. So why is this reaction not considered? This was just a general question, but we'll answer it anyway. Why is this reaction not considered to be environmentally friendly? Because it releases carbon dioxide, which is, it releases, if you remember very well, carbon dioxide is not CO2 of the gas, which can be harmful to the environment. That's all they were asking you. Typically, in a case like this, all your answers lie in the given chemical reaction. Why is it not very friendly to the environment? Because remember, carbon dioxide is one of those gases that damage the environment, such that there are even taxes. Companies actually get carbon emission taxes as well to reduce their carbon emissions, because eventually what happens is it kills the ozone layer. Right, it's one of those gases, not very good. So sometimes they plant trees to make sure that they absorb it and so on and so forth. So it's not a good gas, basically. Yeah, so that's why this reaction is considered not to be environmentally friendly. It's not an environmentally friendly reaction. So that being said, I wished we could do more of these past papers, especially for this one, but you guys are more than welcome to actually send your questions on the group. Whatever questions you have, especially if you want to do past paper questions, please send them, and then we will gladly assist you. And then this brings us to the end of today's lessons. Right. Can't believe bonds. Right. Yeah, I think that's we've covered everything, guys. And thank you very much for attending. And see you again on our next lesson. So remember, if you have a question, you are more than welcome to ask. I think someone is asking a question. I'm not sure. I think it's Tando. Tando. Tando, I can't hear you. Please repeat if you're asking.